Thanks everyone for coming. Looks like we have a pretty good group of participants. This is Jesse from the UNP office. I also have Beth and Mike with me today. So just wanted to kind of provide a little introduction to EATs in general. These EATs, we're going to start out with the higher level stuff, systems engineering, mission definition, things like that, and then eventually work our way down into the kind of nuts and bolts, all the individual subsystems, even some stuff that you won't see in phase A, like operations, but that you may need to consider. And one other note on these is there's lots of advice. They're pretty much all going to be provided by subject matter experts. Lots of advice and guidance, but you know, this is to be taken with some critical thought, right? We can tell you kind of things we've done. We can tell you things we recommend, but it may not apply equally to all your missions because of the nuances of your specific mission. So, you know, these are not directives on things to do, but they are advice and guidance from those with experience. And that, you know, certainly you can ask questions about those if you're unsure on some of those details, but the goal is, you know, make sure there's critical thought applied before directly taking any of these word for word. So with that, the topic of today is systems engineering. We're going to have multiple parts of systems engineering that are a little bit spread out over the coming weeks. These will be given by myself and potentially some others. But yeah, today we're gonna dive into kind of a high level introduction to systems engineering. So let's get started. So, you know, quick agenda up front. Purpose of this EAT. What is systems engineering? Some nuances there. How various people do it. How we do it. Some key terms from it, and then of course, you know, what does it mean to you guys? I'll start out by saying this was very heavily taken from the NS10 EAT on the same topic. There aren't a lot of differences from the last one, so definitely significant credit to the author of that one, as well as all the resources that he pulled from. And many of these resources are available online if you are looking for other resources yourself and trying to learn more about this. A few I'll point out. You know, obviously the UNP user guide, that's the major one we provide to you. Some other really common ones that you'll see, the NASA Systems Engineering, of course. And then Space Mission Engineering is a very common book for satellite design and engineering. You may also hear that referred to as SMAD, Space Mission Analysis and Design. Space Mission Engineering it's the new SMAD, it's called. It's just a newer version of that book, but that's still kind of the same thing you'll hear referred to as SMAD. Those are all certainly very common resources, and then there's many others. So what is the point today? Well, systems engineering is a massive topic. Lots of our undergraduate courses don't dive into systems engineering in any detail. Certainly there are some graduate programs, you know, a lot of undergrad programs may touch on it lightly, but it's typically not taught heavily at universities. It's a massive topic. It's, you know, I'm here trying to teach you guys the basics. I certainly am not the perfect systems engineer or the ultimate systems engineer myself, but I do have some experience with this, and I'm able to, you know, tell you kind of what we expect from UNP's perspective. There's lots of different takes on what systems engineering is as well, or what a systems engineer does. So I'll introduce you to a variety of those, but then it's kind of up to you to determine exactly how it will fit into your team from the perspective of your mission and within the constraints of your university. I would say at the core of systems engineering, one of the big things is, you know, how do you go from a concept to something real? You know, you have a proposal, you have the user's guide. Now it's time to build a satellite. Building on what I just said, there's lots of different definitions of it. A few I've pulled out here. NASA, INCOSE is a major systems engineering organization. Johns Hopkins offers graduate degrees in systems engineering. So that's what these three are from, and there are certainly others out there that have their own flavor. You can see in bold some of the kind of consistent themes throughout. Like I said on the last slide, one of those themes is realizing a successful system and getting there from kind of an idea or a concept, and how you turn that into a real system. Another one you'll see is kind of meeting constraints, right? Meeting performance, cost, and schedule goals, while also meeting the needs of the customer. And the final kind of trend you'll see here is the multidisciplinary. It's certainly a need for the subject matter experts to dive deep into each individual topic, but the job of a systems engineer is to be more of a jack of all trades and to understand where you can give and take across those different areas of expertise. So in the bottom, you can see it certainly is applied across pretty much all industry building products and takes into account the full life cycle of a product. A few more terms we can dive into on this. What is a system? Well, modern engineered systems are incredibly complex, right? That if you look at that picture of the car with all of its parts, and even that's not broken down all the way, right? Those seats definitely have fabric and foam and the structure and everything holding them together. So those already had some engineering put into them and are built of other components. So everything gets incredibly complex, and determining how you design each of these individual parts that they come together to make this functioning car that works as a car, that doesn't break down easily, all the good things you want out of a car. How you pull that all together is the practice of systems engineering. It's informally been practiced kind of forever, right? There are certainly large, complicated projects throughout all of ancient history, but certainly it is more formalized now than it likely was then. And not only do we have all these parts, we have interactions, we have other things to consider. And like I said before, the systems engineer, has to consider all of these things: electrical, mechanical, thermal, software, right? Lots of different interfaces across lots of different systems. It's not just being a subject matter expert in one thing. A couple of comics that kind of can help point out some of these concerns, right? When we are an expert in something, we want to make our piece of it the best it possibly can be, right? But when you bring it together with everyone else's, that's the best it possibly can be, you're probably not going to end up with something functional. So it's a systems engineer's job to sit back and say, how do we take these different pieces? Where do we give and where do we take, and what does each person get allotted or each team get allotted to do with their system? And then to come together to make, in the case of the last comic, to make an actual airplane, right? None of these airplanes probably would actually work at all, right? They're all too focused on their one unique area of expertise that they want to push for. The one on the right, gets a little bit more into the interpersonal pieces of engineering. Systems engineering, creating a product that the customer wants is not just about, does it fly well, if in the case of an airplane and those things. It also matters if it met the expectations and goals of the customer, and there's other interpersonal relationships and interactions that have to be taken into account with any real system, right? How do the user interfaces, the design of it, just explaining what you want. A lot of customers may not be technical people and may not even be good at explaining what they want in lots and lots of cases. So there's certainly a human aspect of this as well. There's certainly a human aspect, and that's kind of one of the first things we'll call out here is to be an effective systems engineer, you need to understand that how people work to some extent, and that people matter when you're trying to design a system. Whether it's the user interface side of people trying to use the device you created, or just on the kind of personnel management side of, making sure not every team creates just their ideal piece without considering what other teams need to do to make their parts. The systems engineering role also, frequently is the one that sits at the higher level and looks across the systems and decides where to give and take. Throughout the life cycle of a project, more information will be gathered, as you develop it, but there's lots of critical decisions that have to be made early on when not all of the information exists yet. And so that's certainly one of the key roles of a systems engineer is understanding enough of each system to make an educated decision in the absence of complete information. Linear systems, so in terms of the system development process, are not truly linear. Well, ideally everything would be kind of the waterfall development method, or some do this, then do this, then do that, then do this. But in reality, that's really never going to be the case. And you kind of have to account for that up front. When you start designing a system, typically it's not going to turn out exactly how you expected. And so there's going to be some iteration to adapt. Maybe your initial goals have to be changed, or maybe you have to redesign it to meet those initial goals if they're not very flexible. But overall, this is going to be a cyclical process. The lead systems engineer or chief engineer is definitely going to be the ultimate authority on how on those give and take decisions, and how in this case, programmatic integrity and technical goals and integrity can be simultaneously achieved, right? There's always other constraints and requirements, and a systems engineer job is not just to look at the technical ones, but to also consider the programmatic, cost, schedule, other pieces as well. Technical risks, making sure you understand the risks, which ones are worth accepting, which ones need to be mitigated, things like that. Right, best performing system. So again, if everyone had their way and made the best subsystem, it likely wouldn't result in the best overall system. And so the goal of systems engineer is to pull that best overall system out of the balance of the other systems. And kind of the last one, right? Measure an effectiveness not by spectacular successes, but absence of difficulties. That's certainly true to an extent. If things go smoothly in a very complicated system, that's usually difficult to achieve and definitely a measure of success. So, overall, systems engineers need to lead the realization of an operable system that meets requirements within imposed constraints. If you've learned anything about systems engineering, you've likely seen the V of systems engineering. This is kind of one of the first things that people will show, as I am now. This is certainly a good initial way to think about systems engineering, but there is a lot of nuance that we'll get into later. But how it works overall is kind of upper left, you're doing your concept exploration, understanding where you want to go with your design, what your mission is going to do. As you work down that left side, you're breaking down those high level goals into more detailed things. So you start out, with just your concept, and then you get into more of the concept of operations, how we're actually going to use it. That's going to flow down into requirements, subsystem requirements, right, all the way down to the component level. And then at the bottom is where you build stuff, and then you work your way back up the right side, checking that everything you did on the left side worked. And you check again at every level until at the top, now you have the fully integrated functional system. And of course, it could move into kind of ongoing maintenance and things. But certainly a good way to start thinking about this, and then we'll visit a lot of the nuances of it in later slides. One of the things that we like to do as engineers, in all of our courses, one of the reasons we probably got into engineering is because we like turning bolts and writing code and blowing up our circuits that we designed poorly or something like that, right? We like digging into the nitty gritty and doing the detailed design. But the problem with that is if we go there too soon, then what we wrote, the code we wrote, the CAD we designed, whatever, likely won't be correct for the overall integrated system, right? We have to understand the give and take of the fully integrated system before we can actually design our part to meet that. And so doing all this stuff, this work on the left side, well, it may seem annoying at first, is actually very, very critical to realizing a fully functional system. One way to think about it is that the true design is actually occurring on that left side before you ever even get into the detailed nuts and bolts of it. For those of you who attended the mission design class here at Kickoff the other week, we kind of went through some of this higher level stuff, right? And the design, there was still some actual design work done on this left side, right? We were doing some of the feasibility power budgets and data budgets, link budgets, all those early feasibility studies and analyses to say, yes, this will work before we actually just decide on something. And that's kind of what a lot of this higher kind of upper left portion of the V is getting at. I mentioned on the right side of the V that you're going to do all the tests to make sure everything works. And so this is an important topic in systems engineering. So it's something I want to talk about in a little bit more detail. You may have heard the term V&V, or verification and validation. And at first glance, it might seem, like those are the same thing. What's the difference there? In terms of systems engineering, they do have different meanings. And they kind of come out of the quote at the top there is kind of one way to think about it, and then there's some other ways to think about it. But neither the world's greatest design poorly implemented or a poor design brilliantly implemented is worth having. And so one of the very common definitions, the short and sweet one there that you'll hear is verification is, did you build the system right? Validation is, did you build the right system? And those aren't quite the same. If you think about building the system right, on those bottom bullet points, well, we're going to have requirements, right, that say it has to perform at this level. did it perform at that level? And validation is a little bit more fuzzy, but it tends to come back to the stakeholders, right? When you hand this doohickey to a stakeholder, the person who asked for it in the first place, are they going to look at it and say, yes, this is doing exactly what I wanted it to do? Or is it not meeting what they expected out of it? A couple more, things we can get into to kind of emphasize this. Well, so in all of these cases, these are all verification issues. We built the right system. We just didn't build it right. So, the bridge there, right? It's still a bridge. You can even see the vehicle driving on it. It's doing its job, but clearly there was a screw up because the two halves of the bridge are not aligning. And that's kind of the case with all of these, right? They built the right system. They just didn't build the system right. And so it's not meeting requirements. It's not going to be a functional system. A couple more examples kind of straight out of space, the space world. Most of you who've been interested in space for at least a few years have probably heard about a bunch of these. NASA Genesis, for example, was sampling in orbit. It had a return capsule that was bringing the samples back to Earth. That parachute did not deploy on that return capsule, and it smashed into the ground, and most of the samples were destroyed because it smashed into the ground. The subsequent investigation found that it was most likely an accelerometer was installed backwards, which is what led to the wrong data, of course, and the lack of the parachute deploying. Hubble, almost everyone is aware of Hubble's mirror that was out of focus, right? And in that case, it was actually the test apparatus itself that was wrong. And that was, of course, a huge debacle to fix. And Mars Climate Orbiter, this is always the one we hear about in terms of units, right? The software, there was a miscommunication. Software didn't take into account the units conversion between English and metric units. And because of that, it performed its reentry burn incorrectly and entered into Mars' atmosphere and burnt up. It was supposed to orbit Mars, and then the burn was supposed to put it into orbit around Mars. Now, on the other side, the validation issue, in these cases, the system was built right. The goal of the system was met, but the system itself didn't have good reason to exist in these cases. So Juicero, this one was from a while ago, a huge startup. It was one of those things that kind of went viral. They made these really exquisite machines that pressed these bags of juice to take advantage of the healthy diet market. This machine, it cost the consumer $700, and some of the articles I've read said that was likely still a loss to the company. They made this machine so complicated and expensive just to press juice bags. Well, it turned out you could actually press the juice bags by hand, and they were trying to make the money back, on that subscription for juice bags, but at the end of the day, it didn't make sense at all, and the company eventually dissolved. Google Glass, many of you may be familiar with that as well. Hugely expensive product with basically no actual problem that it was solving. And so overall, it didn't actually meet what customers wanted, what stakeholders or customers were looking for, because nobody was really looking for this. And so it was not a successful product in the end. So those ones both kind of make sense. This one, first glance, may seem more like a verification issue. This might seem more like, oh, it didn't meet the requirements. But in fact, this is actually a missing requirement, which falls under validation. This was a case of a bridge that ended up having a resonance mode that was in tune with the frequency of people walking in step. And then that actually exacerbated the mode because the people walking in step made it even worse. And so it created this huge sway with a lot of people on it and took a bunch of money and time to fix. We can get back into a variety of systems engineering topics. Well, I showed you kind of the V. That's one of the most fundamental, what everyone shows for what is systems engineering. However, like I said, there's a lot of nuance to that in terms of how you actually implement it. So a lot of large organizations will take and develop their own approach to systems engineering. This is certainly not something every organization needs to do, but in the case of NASA, being a massive organization, they have developed their own approach to how they actually do systems engineering. And they call it their systems engineering engine. This can certainly be found online. One of the kind of keys here is, NASA mostly does very large satellites, very large space vehicles. And so this approach is tuned towards that. Whereas in CubeSat world, we tend to do smaller, cheaper things and accept a lot more risk. So certainly this can be good background, but if you do dig into the NASA systems engineering standards and engine, definitely keep in mind, who this was written for. And if you do look at this closely, you'll see that it does align, somewhat well with the V. It's not formed like a V, but on the left side, if you look at all those things, it's a lot of the same processes that go into it, where you have the flow down on the left from high level concept down to the decomposition down into designing. On the right, it goes back up the other way with the verification and validation. And in the middle, you have all of those technical management and verification, validation plans, risk management things. So overall, it is heavily V inspired, just laid out a little bit differently. So what do we look for in UNP from a systems engineering perspective? Well, one of our major goals of UNP is systems engineering education, turning all of you into effective systems engineers to enter government, enter industry, and do this well, because good systems engineering saves money, creates effective systems. Good systems engineers are incredibly valuable to everyone. So that's our primary goal for all of you. We'll start diving kind of down into the nuance of what that looks like from a UNP perspective. Certainly the user guide is a good place to start, but here's just a little bit. So what I've done here is taken that V that I showed you earlier, that was one that came off of Google, and just renamed certain things in it. So if you look, there's some of the names might look a little more like the user guide names now, where we have your proposal on the upper left, mission definition, then kind of the requirements down to unit level. So this is just a little bit rewritten into UNP language, but overall this is still the same V. There might be a few things in here you don't recognize yet, but we'll talk about them either today or in future EATs. However, this is not gonna fit in perfectly. So to some extent, that this does align with your reviews, the reviews that UNP requires. These are certainly not perfectly aligned, and there's certainly going to be go backs at times, but you can sort of start to think about it in terms of these reviews. But like I said, this is actually not going to be a perfect view of how you're going to do systems engineering. One of the reasons is that, like we already said, development is almost never linear. There's always going to be these balances between, you come up with an idea, you analyze it, oh, part of it isn't feasible, well, let's change the idea or do more analysis to see if we need to come up with a better device to meet that initial analysis, the initial idea. So there's lots of recirculation that happens. And on the right here, you're seeing one of the higher level things that we do here at AFRL in the small satellite portfolio. And that's where the right side graphic came out of. And so you can see on top, we start with the mission objectives, constraints. You do the design build iteration. That's kind of getting at like the mission design class we held, where it's more the high level analysis. Peer reviews are certainly very valuable. That in your cases, we're going to come hold reviews with you. In the case of a mission here at AFRL, we will hold reviews with our branch, with other branches, stuff like that, to get the peer review and find things that you may have missed. At a higher level program, right, there's a budget. You need to make sure that what you're doing matters compared to other things that may matter less. So assessing what you're doing and the level of effort required against the constraints and the goals of your program, and then ranking and executing. So that one's a little bit more specific to the small satellite portfolio because we have multiple missions. And so at the branch level, you're trying to manage which missions matter more or less, whereas in your cases, you'd maybe take that a step down where it's you have your one mission. You are certainly going to do some work on figuring out what matters for that mission to do, but then within that mission, maybe there's subsystems and other things where you have a priority of how you go through that work. And then again, in step 6 on the right, the programmatic piece, certainly valuable for you as well. It may apply a little more to the bigger branch. And you can see that in both of these, there's actually 2 separate kickbacks, right, to understanding those feasibility studies and there's an inner one and an outer one and so that's just getting at the fact, like I said, a lot of it is not very linear. Another thing that changes a lot from the strict V is the V assumes, okay, I figured out my mission. Well, now I'm going to break it down into requirements, and then I'm going to design it and go up the right side, and we're going to meet all those requirements, and it's going to be a good day. The reality, in addition to the cycling on just understanding your definition, the reality is that there are always constraints, especially in a university environment, right? You have cost constraints, technical constraints, just the resources of having, you only have students, they're only there for a bit of time. there has to be significant recognition of those constraints, and that this likely won't be a strictly requirements-based systems engineering. It'll be a mix of requirements and constraint-based systems engineering. And the V tends to lean much more heavily towards pure requirements-based systems engineering, where you have some, maybe you have some constraints, but they're less noticeable. And in the case of your missions, you have to recognize those, and they are going to play an important role. This is just getting a little bit more at the go backs. And so you can see, you come up with the concept and the mission design, and there's going to be a lot of analysis and feasibility studies. As you get into more definition, you're going to learn more about your system. Well, that's probably going to cause some scope changes and constraint updates and things like that. Of course, once you get the real hardware, then you're going to learn even more, and that may flow back up. In that case, by the time you're over on the right side of the V, well, your mission definition should be probably pretty well set. There may be opportunities if things go really wrong to change that. But one of the other things that you may change at that point more is like your ConOps. How does this get used? Your concept of operations, how does this get used by the user? And are there changes we have to make to how we approach using it because of some limitation we found in the actual system's function? And so that would probably be more where the right side circulation would occur, rather than going all the way back and changing your mission definition. But that could happen if there were serious issues that resulted in it, which is something that we'll talk about more in future ATs, I think. One of the things that you'll see up on here that you may not recognize is the systems engineering management plan, some technical management things, right? Like I said, right now, you guys are just starting, so you're all up on this upper left side of the V. Next week, we're going to have a presentation from Dr. Lauren Hunt on mission definition, so that'll cover that chunk, but we'll talk just a little bit about the SEMP today. The Systems Engineering Management Plan is not a required deliverable to UNP. And the reason for that is this can vary greatly across teams and across your mission. So what this is getting at, though, is you have to have a plan for how you're going to approach this. In some cases, that plan may not need to be super formalized, that plan or written down. It may be, if you have a really small team of people who know what they're doing, maybe that plan is more just understood. If you have a huge team, well, you probably need to formalize that and make sure everyone's on the same page with the plan. And so there's a lot of questions here that can kind of help you think about it, but at the high level, right, how do you keep the resources you need, personnel, scheduling, how are you scheduling things? How are you managing risk? How are you managing, quality assurance and like document configuration management? All those different things would be pieces of a systems engineering management plan. And so, the bigger the organization, the more detailed this probably needs to be to ensure that continuity and understanding across the lab. But this is certainly something we'd encourage you to think about and formalize to an appropriate level for your lab and your team. I already kind of mentioned this, the mission definition EAT will be next week. This is where you guys are kind of at in the process right now. In a month or so, you're going to have your system concept reviews, which will be our chance to review where you went with mission definition, but that does not mean that you should be starting mission definition at system concept review. It means you should be doing it now so that we can review and ensure you're in a good place at the system concept review. One of the things that I'll touch on related to this is the mission design document. So this one is a UNP requirement. You will be expected to deliver this document at pretty much every review, and it will mature, of course, over time. It won't start out with the full detail. And what we've done with this is kind of included what in some cases may be 3 separate documents. So the mission overview is going to be more your story to stakeholders. It's the how do you explain your experiment to someone, your mission to someone who's interested and who hasn't heard about it before. The experiment plan gets more into the details of collecting your data, how your experiment's going to go, your payload, the details of your payload, more the sciencey piece. And then the ConOps is the overall, how are we going to fly this thing? What does it look like more from the user interface? So these are all certainly things that'll be discussed in more detail, and there's a lot more detail on them in the user guide. So I definitely recommend you look there, because this is one of the first documents that UNP is going to require of you. I've talked a little bit about flow down. This is again something that mission definition will get into the next DAT, but one of the things that you frequently see in systems engineering is in order to create that, I have high level objectives, and then below that I have high level requirements, low level requirements, that there should be this clean flow down in systems engineering. We'll talk a lot more about requirements in the second systems engineering EAT in a few weeks. But this is just kind of the hint at, you're going to have some mission statement, you're going to have some mission objectives. Eventually, you need to get to the level where you can go design your detailed boards, your detailed circuits, whatever, and make sure that they meet that as those flow back up, you're going to meet your high level mission objectives, your high level mission success criteria, and ultimately your mission statement, which is more the validation piece. How this flow down works is very important to track. And you certainly want to make sure that, as you are doing all the detailed level things, they're supporting the higher level pieces, right? You don't want to be, off it down a rabbit hole doing something that has no impact on the higher level objectives, because that doesn't support the mission in any way. So you want the flow down is certainly important, but there's also the reality, like in everything, there's nuance to it. So there will be UNP requirements that come in at a variety of levels. If you look at the user guide, you'll see something like, exactly how many, I want to say it's around 70 or 80 requirements that UNP levies on you. Some of them are at the higher mission level, some of them are lower. So those may be side-loaded into your requirements matrix at various levels. Stakeholders may have various constraints and expectations, and certainly just the university environment will have constraints and expectations that could sideload at various places. One example may be you already have a ground station, and so you're going to make your satellite radio and systems work with that ground station, and those constraints from that existing ground station is going to probably flow in at various mission subsystem and subsystem level requirements, right? And that it's going to affect when you can schedule passes and the orbits you need in order to see that ground station at the mission level. And it's going to affect, what radio you can buy because of certain modulation or powers or whatever down at the subsystem level. So it may not be a perfectly clean system, but making sure you understand and are keeping track of these things is important. UNP is going to impose various constraints on all of you, right? Schedule, obviously, we're holding you to. We're only giving you so much funding, and you can certainly go find funding from other sources as well. But at the end of the day, there is a funding constraint on you. It's not unlimited. And then the user guide, like I said, the user guide has a ton of requirements that we levy on you. And those are not meant to make your life difficult. They're actually meant to make your life easier, because they all come from lessons learned over time, whether it be missions we've flown here or university missions. If you stick with those UNP requirements, then it will make your life easier down the road, as you won't run into as many roadblocks from various policy or technical concerns. Some are related to launch vehicles, some are related to just making your system more functional. They're certainly not meant to make your life difficult. They're meant to make it to help you. A few more constraints. So I've already touched on some of these as well. One of the big ones is just working in a university environment. You have students who are doing all this work, which means limited experience, limited time, right, and high turnover, losing a lot of your most experienced students all the time. So that's always a huge one. If you have stakeholders, they may have other constraints they apply to you, and then of course I already mentioned the cost and the technical and schedule ones from UNP and our funding sources. And this is also not all encompassing. There certainly can and likely will be other constraints on you as well. Just a few more definitions as we're getting close to the end here. Stakeholder tends to be, it could be just about anyone who touches the system or has impacted the system. UNP frequently looks at stakeholders for your missions as someone who can help you determine why your system matters and why you should do it. So, if there is a government agency or specific personnel somewhere who has an interest in your mission and can help you understand why you should do it and how well you should do it, that can be very valuable to you. Of course, it can also be very difficult for you to work with those people. But, when you're trying to get a satellite flown into space, you have to have some level of justification of why you should get funding and why you should get a slot to go to space, because it is not super cheap and easy to get to space. So that's one thing that a stakeholder can be very beneficial for. But there's certainly a variety of impacts or ways you can define stakeholder. A few more things, constraints. So I've already talked about these quite a bit, but overall a constraint is something that's limiting you in some way that you can't really get around. The mission statement, UNP are required, typically views this as like a multiple sentence statement. The user guide kind of goes into a lot of these different things. Mission objective. So this is kind of what you want the system to do. You can see this comes from SMAD. That's that Space Mission Analysis and Design text that I mentioned earlier, now called Space Mission Engineering, or the new SMAD. Success criteria are more the how well the system must do it. They should have quantitative values in them versus the objective, which is probably more qualitative. And then the ConOps, concept of operations. So this can be a complicated one. I would certainly encourage you to go look at the user guide for it. But at the high level, it's kind of like the characteristics and how you interact with a system from the perspective of the individual who will use it. Certainly go dive more into the user guide for this, and then this will be touched on more next week at the Mission Design EAT as well. Just a quick taste of what you're going to see next week. Mission definition. So this comes out of the NASA Systems Engineering engine as well. But how do you come up with your mission? How do you determine it's a good mission? How do you determine it's feasible? This is a very cyclical process, and you can see it goes through quite a few different steps that each are not super simple themselves. Those of you who attended the mission design class at kickoff, this is what we were trying to give you a taste of, was this picture here, basically. So this is certainly something I'd encourage you to go start looking at right now, because this is something you should have made at least a few iterations on before your system concept review. And so just to kind of foot stomp, this is something that you definitely need to start doing now if you haven't already, because it's never one and done. This takes iteration to get to the right answer. Just one more little kind of broad, what is this going to look like? So next week is going to be the mission definition EAT. There will be a systems engineering part 2 EAT that'll start to dive much more into requirements and how we define those. Systems engineering 3 will look a bit more at the philosophical side of validation, verification, planning, managing stuff. And then we have a lot of other EATs. Most of them will be more on the bottom of the V, the kind of details of subsystems and things like that. But a few of them will climb up the right side and get into verification, validation, even a bit into operations. And even though you certainly won't be, anywhere near doing those things yet, especially the operations, there are things you can do now as you design the system that will make your life a lot easier when it comes time to do those operations and things. And so that's what we're trying to help you with in these EATs, is helping understand the knobs you can turn now to not have people in the future be mad at you for the choices you made. So, like I said, this was just a brief intro to systems engineering. It's a massive, massive topic. The user guide has more info. Certainly you can ask questions and either now or reaching out to us via email. Like I said, there's the list of resources, but that's what I have for you today. So I will take questions.
I had a quick question regarding,
Yeah.
So I believe this is part of the systems engineering management information. I was taking notes during the thing, or project management plan. Or one of the questions that we were told to think about is, how do we train new members and how do we keep team members accountable for the projects that we're working on? And so I was just wondering, what would be an approach to that? Because at the university level, we can't really afford to give people salaries, and the only real incentive we have is students being internally motivated to do their stuff. But that's not necessarily something we can expect from everyone. So I'm just wondering.
Yeah, that certainly can be challenging. It varies by university. Some universities, there may be paid positions. Some universities, there may not be paid, but there may be some credits associated with the course or something that's actually, allows you to hold them accountable to a standard or to an expectation. If you don't have any of those, then it certainly can get more challenging. I think one of the biggest pieces in that case is to make sure that you develop a culture of accountability, right? And ensure that the culture leads people to meet their requirements and isn't passive about, oh, they're only here for a bit and it doesn't matter if they didn't do this or that or the other thing that they said they would do. So I would say that's probably one of the important ways. And then as far as training goes, I think creating formal training plans certainly can be beneficial, especially if you have a large team. Some of the larger UNP teams even have like a semester where new recruits to the team have to do some unrelated project for a semester that walks them through a variety of exercises related to both the general team and then maybe more specifically in the area they're going to be working in the team. You know, those of you who, if you're at the mission design class, that's something that we offer, but that's more on the mission concepting side. But certainly you could think up, you know, something based on that to train in members more specific to your mission to kind of work their way through whatever you want them to learn. But I would say it varies so much by school, so we can certainly provide various tips, but a team of 10 people that's more like a club that's all grad students or whatever is going to be very different than a team of 100 undergrads that, you know, maybe getting some credits for it or whatever. It varies so much across universities that's I can't really provide you an answer, just some tips on various options.
That was very helpful. I'll definitely keep this in mind. Just a quick question regarding like side projects and stuff. You mentioned during the presentation that it's not wise to dedicate a lot of manpower to projects that are unrelated. So how would you, like, where would you draw the line between we're using this to train people and have people get familiar with the general concept of designing a mission and creating hardware and testing versus we're putting too much time into it and now it's being a detriment to like.
So yeah, so I think at the higher like projects available in your lab, the PI level, the lab level management, having other projects is just fine, right? There, you can certainly decide, you know, how you want people to, who's assigned to what projects, how you handle that, as long as you're making sure that each project is adequately staffed. What I was getting at, I may not have said it as well as I could have, but what I was actually getting at was more on like gold plating requirements, or for example, you know, if I have a requirement to be able to point at the ground within, you know, 3 degrees of my target as I fly over, but I have someone who's spending hours and hours developing an ADCS that can point to within 1/10 of a degree just because it's cool to them and they want to do it and do better, but it's taking way longer and making, you know, wasting time and resources. That's kind of more what I was poking at, was less kind of the overall lab management and more making sure that you're not wasting time within the program doing things that don't matter for the program.
Just to confirm, so it was more along the lines of don't over-engineer like this one solution at the cost of the whole program.
Yeah, that's certainly a piece of it. That's usually called gold plating your requirements, or among other terms. Yeah, so, you know, overall at the lab level, right, training someone in with a separate project might be good for the lab and good for the project overall. So that's not necessarily a distraction if it's a net benefit to the lab, but you kind of have to figure out what's best for your lab there and what makes the most sense. Because of course, training people also requires additional manpower from the trainers to put the curriculum together, all those things. So like I said, it's something we've seen done very successfully in very large labs. In smaller labs, it tends to be a little bit less formalized because it's more of a distraction, but you kind of have to figure out what works best for you.
Thank you. It was a good presentation.
Of course, thanks.